Hello everyone and welcome back to the machine learning revision session. So today I am going to explain you about concept learning, finesse algorithm, version space, candidate elimination algorithm and inductive bias. Now the first topic for the day is with respect to learning task. Say for example we want to make an hypothesis about the day on which the famous cricketer Sachin Tendulkar goes out for enjoying the water sport. Say now we need to find out the right hypothesis, right, from the history data or historical data. So history or historical data means on what days earlier or previously Sachin Tendulkar was going to enjoy the water sport. That means say he was going for swimming. So on what days he was going to go for enjoying the water sport means say probably on a sunny day day 1, day 2, day 3 and so on he was going for the enjoyment of water sport. So that is what we need to find the right hypothesis from the historical data, right. Next, on which days he will come out to enjoy the water sport, these are the attributes which will define on what day Sachin Tendulkar will be going to enjoy the water sport, taking on the some values for the attributes like the 6 attributes. What we have defined here is sky condition, or you call it as sky or sky condition, humidity, air temperature, wind, water and forecast, right. These are the attributes. For those respective attributes we call them as training examples for enjoying the water sport. For all those 6 attributes like sky, temperature, wind, humidity, water, forecast, and the last column is enjoying the water sport, whether you are going to enjoy the water sport or not, that is yes or no. So for the respective 6 attributes you have the specific values. Those specific values are: for sky it is sunny, for temperature it is warm, for humidity it is normal, for wind it is strong, and for water again it is like warm, and forecast is whether it is same or change. Now here in the first row forecast is same. Now if it is yes or the Boolean function is 1, then you need to say like yes, that Sachin Tendulkar will be going for enjoying the water sport. Similarly with second row and the last row. But in the x3 or row number 3, like it has been changed to sky condition has been changed to rainy instead of sunny. So rainy, then temperature is cold, again humidity is high, wind is again strong, water is warm, but the forecast is change. So forecast is change. But enjoying the water sport, whether he can go to enjoy the water sport or not, yes, it is saying like 0. 0 means Boolean function 0 represents no. So on that particular day he cannot go and enjoy the water sport. So we are considering both negative and positive learning examples for concept learning. So C is the target concept here, deriving a Boolean function from the training example so that the hypothesis or hypothetical Boolean function can be arrived at. So hypothesis finding H in such that H will be equivalent to C. That is, C is nothing but the target concept. So other more complex examples are non-Boolean functions. Those non-Boolean functions we will look into those non-Boolean functions later stage. So generate the hypothesis for concept learning from the given training examples. Now representing the hypothesis. So how to represent the hypothesis of going to enjoy the water sport? Say task is to find an appropriate set of hypotheses for concept given training data, right. So which represents as conjunction and of constraints from the following values. So following values will be like specific value will be water will be is equal to warm, then don't care value or any value can be allowed is question mark symbol. These things we have defined earlier also in the previous session, class sessions. So no value will be allowed, will be like water will be is equal to null or empty. So that is no value will be permissible given values of the for the given values of other attributes. So use a vector of such values as hypothesis such that sky, then air temperature, humidity, wind forecast, etc. are represented with the values like sunny or question mark symbol is like any value can be allowed, or you call it as don't care value. Then strong is a specific value, again question mark symbol, again same is a specific value. Then here we have an satisfaction hypothesis, that is nothing but you call it as example which satisfies the hypothesis, which is defined as function of h of x. So h of x is equal to 1 means if h of x is true on x, then it is satisfies. Otherwise if it is 0, then it is not satisfied. That means if h of x hypothesis of the instance x is 1 means it is true. True means you can go for enjoying the water sport, that is satisfiable. So if it is 0 means you cannot go for enjoying the water sport on a particular day. H of x will be negative. So you want an hypothesis that best fits this example, that can reduce the learning to such a problem over the space of given hypothesis or given space of hypothesis. Now the typical concept learning task will go like this, like task is to predict when the person will go to enjoy the water sport, such that the target function is C, enjoying the water sport with the instance x will be the boolean function 0 or 1. So it cannot be in general to know that the target function C where then we need to adapt for the hypothesis H about the concept C. From the hypothesis H, there are conjunction of literals like whether it is generalization or whether it is a specific value like cold or high, and again the generalization which are the allowed values. Then you need to learn this by experience. So earlier we have discussed what is task. Task is T. Then next one is experience. Experience is E. So experience E is nothing but the instances of x which are on all possible days described by the attributes like sky, air temperature, humidity, wind, water and forecast. So the training examples will give you the positive and negative examples of the target function with the data set from x1 to xm, right. So concept learning of x1, concept learning of x2 and so on for up to concept learning of xm. Last thing is performance measure. So performance measure P is how do you measure the performance by hypothesis. So hypothesis is small h in the big H, right. So that is hypothesis THESIS, small h in the capital H is hypothesis out of all those hypotheses such that h of x will be is equal to C of x, that is hypothesis of instance x will be is equal to the concept learning of in the instance x for all the instances which are there in the given data set D. So there might be existing several alternative hypotheses that are best fit into these examples. Here are the approaches to learn the algorithm. First approach is like brute force search algorithm. This is one of the enumeration and possible hypothesis for evaluation. Say here you will be having 96 distinct values for the given instances x. Say for sky you have 3 specific values, for rest of the attributes you will be having 2 specific values. Say for sky you have sunny, rainy and cloudy are the 3 specific values. Say for rest of the attributes like air temperature, humidity, then forecast, water, etc. you have strong, normal, weak, cold, etc. Only 2 specific values. Out of these, if you take all the instances of all the specific values for the 6 attributes of the instance x, then it will be 96 distinct instances. For the syntactically representation of the distinct hypothesis, that is zeros and question mark symbols. Zeros means it is a null value. So then enjoying the water sport of the hypothesis H will become 5 into 4 dots, mean 4 dot 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 4 dot dot 4, that means 5 into 4 times 5, that results in 5120 distinct, syntactically distinct instances. Then in fewer cases we consider H with zeros. Every H hypothesis with an empty set of the instances will result in a semantically distinct hypothesis, that is 1 plus rest of the specific values will give you the resultant of 973 semantic distinct hypotheses. So where enjoying the water sport is very small problem compared to many other problems. Hence we have two approaches here. One is search based on ordering the hypotheses, another one is searching based on finding all possible hypotheses or hypotheses using a good representation of hypothesis space. So all the hypotheses that will be fitting in the data. So first approach is ordering on hypotheses. So how do we order or we will keep the ordering of hypotheses? That is, on the left hand side you have instances X, on the right hand side you have hypothesis X, where generalization will go to bottom and specific values will go to the top. So on the left hand side of the instances you have X1 and X2. X1 is sunny, warm, high, strong, cool and same, and X2 is again sunny, warm, high, weak or light, warm and same. Then on the right hand side you have the respective hypotheses H1, H2, H3, which are represented with the specific values and general values. So specific values are sunny and strong and rest of the values are general values. In H2 only sunny is the specific values and rest of the values are general values, and in H3 sunny and cool are the specific values and rest of the values are general values. So you can check from the hypothesis H to instance X how H1, H2, H3 has been mapped with. So H is more general than H dash, that means H is greater than or equal to the generalization of H dash if for each instance X. So H dash X will be equal to 1 such that H of X will also be equal to 1. So which is the most general or most specific hypothesis is the next question we need to answer by using the find S algorithm. Now we have discussed in the earlier class session also what is find S algorithm. Again here we need to check for which is the most specific hypothesis, that is find S algorithm. Assumption is like there is an hypothesis H in the hypothesis H describing target function C and there are no errors in the training examples. TE means training examples. The procedure goes like this. You need to initialize the H to the most specific hypothesis in H, like for what is this means you need to initialize with all empty or null values. For each positive training values then of the instance X, then each attribute constraint AI in H will be like, if the constraint AI in H is satisfied by X, then you need to do nothing, it will not be changed. Otherwise you need to replace AI in H by the next more general constraint, right? Next more general constraint will be a question mark symbol that is satisfied by the instance X. So the output of the hypothesis H will be obtained. So assumption here is like everything except the positive example, other examples are negative. Now if you consider the same example of find S, now here x3 is negative and we are considering only x1, x2 and x4 as positive examples where h0 is initialized to null values. Null values means initialized to empty sets, which is more specific here, right? H0 is at the top means which is more specific, but which has been initialized to null values or empty values. The drawbacks in finding S algorithm. So what are the drawbacks in finding S algorithm? The problems are the information is always a throwaway. That means it will be excluding the negative examples. It will not consider the negative examples, and we cannot tell whether it has been learnt from the concept or it has learnt the concept. Depending upon the hypothesis, there might be several hypotheses that fit into the training examples. So picking up a maximally specific hypothesis, whereas you will not pick up any other hypotheses. Right, only why we need to pick up the maximally hypothesis of H means because we are considering only the positive examples and we are not taking any negative examples. So again, it is very difficult to tell that when the training data is inconsistent, so we need to ignore all the training examples. But it is very simple when we consider only the positive examples. Outcome is independent of ordering of all the examples because it is ignoring all the negative examples, and it will be marking with, or it will be considering the boundary of only the positive examples. Now, how to overcome the problems of this find S algorithm? By keeping all the consistent hypotheses. For that, we need to go for candidate elimination algorithm. So consistent hypotheses and version space. So before telling the candidate elimination algorithm, again the same thing what we have defined with the example of iPhones in the class session of candidate elimination algorithm, right? So version space and consistent hypotheses are defined like this, and hypothesis H is consistent with a set of training examples of data set D of the target concept C if hypothesis H is equal to concept of H for each training example instance X and the concept X in the data set D, and noting that the consistency is with the respect to the specific data set D, right. So here we are going to define this in the notation where consistent hypothesis H and the data set D for all the instances of X of the concept X belongs to the data set, right, and it will be equal to the same hypothesis of H will be equal to the concept of X. Now the version space VSHD we have defined earlier also with respect to the hypothesis space H and the training examples D is the subset of the hypothesis H and the consistent data set D. So the notation used is here is VSHD where H will be belonging to the hypothesis H, right, along with that it will be consistent to the hypothesis and the training data set D. Next is list then elimination algorithm. So the list then elimination algorithm is defined in easy 4 steps, that is version space VSHD lists all the hypotheses in the H, right. It will list all the hypotheses which are present in the hypothesis H. For each training example of the instance X and the concept X, we need to remove from the version space any hypothesis H for which it does not belong to the hypothesis X and concept X. So where H of X is not equal to C of X, then we need to remove it from the version space. Then the output list of the hypothesis will be the version space. This is essentially a brute force procedure to list the elimination algorithm. So here we can revisit the same find S algorithm with the example of the instance X and the hypothesis H from generalization to specific with respect to instances X1, X2, X3 and hypotheses H0, H1, H2, H3 and H4. X3 is marked with the red color rectangular box and H4 is marked with the blue color rectangular box here, saying that X3 is the negative one and which is outside the positive circles, right, of X1, X2 and X3, right, and H4 is excluded here and you will be X4 is sunny, warm and strong which will be mapped to X4, that is the outermost circle of the instances X. Now better understanding of the version space of in this example is Sunny, Varam and Strong but the end result of that is the specific values, but the generalization values will be like Sunny and Varam, which will be defined at the bottom layer. So the first level is Sunny, Varam and Strong as specific values. At the bottom level it is generalization with respect to Sunny and Varam, and rest of the things are generalized. The in between the middle level is the version space. So version space, which consists of Sunny, Strong and generalization. Again Sunny, Varam and generalization, Varam, Strong and generalization. That is, it is the subset of the hypothesis and the hypothesis of the specific values and the generalization. So that is what is called as version space. Now representing the version space by two ways. We can represent the version space in two ways. One is with respect to G. G means general boundary. Another way is S. S means specific boundary. So when we want more compact representation of version space, then we must store most or least general boundaries in the version space and generate all the intermediate hypotheses in version space. So the idea is to generalize from more specific boundaries and specialize from the most general boundaries, or we call it as specific to generalization of boundaries. That means the generalized boundaries or generalization of boundary G of version space Vs H of D is the set of its maximally general members consistent with the dataset D, right? Whereas summarizing that, the negative examples or anything more general will be covering in the negative training example. When we go to the specific boundary S of version space Vs H of D in the set, it covers the maximally specific members consistent with the data set D, and summarization will be with respect to all positive examples. Anything more specific will fail to cover a positive training example. Now the theorem has to be proven. So theorem will be proven in two steps, like every hypothesis H will be satisfying the right hand side of the version space hypothesis and data set. And second step is every member of version space of hypothesis and data set satisfies the right hand side. So what is that every member? Every member of the version space which lies between the specific boundary and general boundary, that is version space of hypothesis and data set which lies between the specific and general boundary, that is the equation. So we can go with the first proving method and second proving method, saying that let GHS be the arbitrary members of GHS respectively with G is greater than H and H is greater than S. So S must be satisfied by all the training examples, and so that H must be more general, and G cannot be satisfied by any negative examples, and so not to be similar to like an, it can be like an H, and H is in version space H of D since it is satisfied by all the positive training examples and no negative training examples. For 2, right, since all the H or the hypothesis are satisfied from all the positive training examples and no negative training examples, so H is greater than or equal to S and G is greater than or equal to H. Now we are going to define that candidate elimination algorithm. So G is maximally general hypothesis in H and S is maximally specific hypothesis in H. So for each training example, so if D is positive, then we need to remove G from the hypothesis which is inconsistent with small d, that is the data set. So for each hypothesis small s in that specific hypothesis H that is inconsistent with that data set D, then we need to remove small s from S. So adding to S all the minimal generalization of H, that is the hypothesis of small s, such that it will be H is consistent with the data set D and some member of the generalization boundary G is more general than the hypothesis H. So that we need to remove from S every hypothesis that is more general than another hypothesis which is present in S. This algorithm we have discussed very briefly in our candidate algorithm session. Now to continue with the candidate algorithm session, so if D is negative, the earlier slide was with respect to D is positive. Now if D is negative, we need to replace G with S. That means instead of removing G from the hypothesis here, for negative example, we need to remove S from the every hypothesis which is inconsistent with D. And for such hypothesis of G in G, that is small g in generalization G, that is inconsistent with the data set D, we need to remove small g from the generalization G and add to the G of all the minimal all minimal specializations or specific values of the hypothesis H of the generalization G, such that hypothesis H is consistent with the data set D and some members of S specific values is more specific than the hypothesis H. So we need to remove G, we need to remove from G every hypothesis that which is less general or generalized than the other hypothesis in G. So essentially there will be positive training examples to generalize specific values S and negative training examples to specific values or specialized values called of G. So independent of orders of training examples will be covered and convergence is guaranteed if there are no errors and there is H in all the hypotheses describing concept C. Now for the candidate elimination algorithm, we can recall the example of same sunny, warm, normal, strong and warm specific values of enjoying the water sport, and S naught will be initialized to null and G naught will be initialized to question mark symbol, that is nothing but general values, and S naught will cover empty values. So if you just check with the D is positive, right? If D is positive, then you can see that sunny, warm, normal, strong, warm, same. Those specific values are positive, which is marked in red color, right? So positive value. So S1 will be like sunny, warm, normal, strong, warm and same. And G1, generalization of specific value 1, right? S1 will be, G1 will be question mark symbols. Now S1 and G1 is been satisfied. To continue, then we have to go for S2. S2 is warm, sunny, warm, high, strong, warm, same. So now if you compare this S1 with S2, S2 means sunny, warm. In S1 it is sunny, warm, normal. In S2 it is sunny, warm, high. So normal and high is the change. So there you can generalize, either you can replace that with normal or either you can replace it with high. So you can generalize there with the question mark symbol. So S2 is again generalized with question mark symbols. Now continuation of the same, we will go to S3. So whereas S3 here the algorithm says, even though it is a negative example, ignoring that you need to go with the positive positive cases, then we will only take the generalization of positive case, that is S3 is also sunny, warm, question mark symbol, that is generalization, and strong, warm, same, which is same as G1 and G2, that represents S1 and S2. So G3 will be the representation of G1 and G2. So G3 will be represented as sunny and generalization, warm and generalization, and forecast will be same and generalization. Now what if another specific value is included? So another specific value included will be, earlier we have discussed with respect to only two specific values for sky condition, that is either sunny or rainy. Now if it is cloudy, then the following specialization or specific values can be used for the next value. So for the next value, then you need to write 3 different values. Then it will become more inconsistent with the specific values. Yes. So the specific values will become more inconsistent here. In such way, so we cannot go for 3 different values, so that we will continue with the 2 specific values. So and last row we will go for S4, and we will denote, or we will define the G4 with the specific values sunny, and rest of them are generalized, and Varam is the specific value and rest of the values are generalized here, right. So why does this example remove an hypothesis from G? That means all the generalization values are represented as question mark symbol, and the forecast is will remain same or it will be changed. So in this hypothesis it cannot be specific, since it will not cover new training examples. That is why it will be generalized. And one more thing is, it cannot be more generalized, or it cannot be generalized because more generalization would cover all the negative examples also. Hence we must drop this hypothesis that if it is not covering new training examples, and if it is not covering negative examples because of more generalization. Now if we take the version space, so on the right hand side corner you can check with that the specific hypothesis and the generalization are there, and in between version space is existing. So already we have discussed this example, like version space is the subset of specific values and generalization. So here, assuming that learner can choose the next training example such that it reduces the maximal number of the hypothesis in the version space, and the best training example satisfies precisely the 50% of the hypothesis, where it cannot be done always, but still, for example, if we consider the positive examples, then it can be generalized to specific values. If we consider the negative examples, then it can be from specific values to generalized values. So now if we are trying to classify the new cases using version space, then we can classify by the procedure of voting procedure on the example. So for the same example, if we do voting procedure, then it will be like sunny, rainy, sunny and sunny. This is how it will be classified in the form of voting procedure. And the effect of incomplete hypothesis space will be like sunny will be either, means sky will be either sunny, or sky will be cloudy, and sky will be rainy. These are the 3 incomplete hypothesis space. So that is what we have discussed earlier also in the class session. If we have 3 specific values per a particular attribute, then the instances of that particular attribute will be it will become into a power set, right. So after first 2 training examples, then you need to cover one more training examples. So first 2 training examples will be positive, then the next training examples will be, or next training example will be negative. Now such that, as I told, it will become a power set. So power set means it will become recalling the same example what I have quoted in the class, right, in the class session. So 96 instances in the enjoyment of the water sport will become 2 to the power of 96 possible hypotheses are distinct values in the full space of H. That means it will become the power set of the distinct instances. Again, if we make it the same, if we take the same with respect to the syntactical and semantical power sets, then we need to make it to 5 training examples. That means 5 training examples means x1, x2, x3 and x4 and x5. So then x5, x4 and x5 gives negative examples, such that S will be disjunction of positive examples and G will be the negation of disjunction of negative examples. In yes, x1 or x2 or x3 will be the disjunction of positive examples, and in G it will not be x4 or x5. So we need to use all the instances to learn the concept. So we cannot predict like training examples have been unanimously or ununanimously voted, or else hypothesis H will be having the precision of 50% vote, or it will not have the precision of 50% voting, right? Whether it will have or it will not have, right? So for every H in the hypothesis H that predicts positive, there will be another prediction that it will be negative also. So unbiased learning and inductive biased learning is the last subtopic of this concept learning. So we have an approach like we need to place the constraints on representation of hypotheses, like example will be limiting to connectiveness of conjunctions, where it will be allowing the learner or allows learning of generalized hypothesis and induces bias that depends on hypothesis representation. So we need formal definition of inductive bias of learning algorithm. So the formal definition is which will be a logically represented system that produces same outputs, or you call it as classification from the inputs. Inputs are nothing but the training examples or instances or data sets, or bias B as candidate elimination algorithm procedure, that is CE. So inductive bias IB of the learning algorithm L is any minimal set of assertions of the bias B such that for any target concept C and the training examples D, we can logically infer the values of C of X of any instance X from the B and D and X. So for example, we will say rote learner, right? So rote learner B will be an empty set and there is no inductive bias. So it is very difficult to apply in many cases, but useful to guide how to apply an inductive bias. So rote learners, there will be no rote learners for inductive bias, and version space candidate elimination algorithm where C can be represented in hypothesis H. For find yes, concept C can be represented in H or the hypothesis H for all the instances that are not positive and that are not negative. So computational complexity of version space is such that S is the set of conjunctive features, vectors and tree structured attributes for the linear functions in the number of features and number of training examples. And similarly, G is the conjunctive feature of vectors and tree structured attributes can be exponential in the number of training examples. So in more expressive language, like both S and G can be now grown exponentially. The order in which examples are processed can be significantly affected for the computational complexity of version space. Last thing is the summary of concept learning is concept learning is searching through the hypothesis H from generalization to the specific ordering of hypothesis H and version space candidate elimination algorithm, and learning the specific boundaries S and general boundaries G, which will characterize the learner's uncertainty. And learner can generate useful queries. And inductive bias, that is inductive leaps, possibly only if the learner is biased. And inductive learners can be modeled as equivalent to deductive systems. Then last line is the biggest problem is inability to handle the data with errors. So far it was very effective for data without errors. Now the biggest problem what we will come across is it is not competitive enough, or it is ineffective when it will come across with handling the data with errors. So overcoming the procedures of learning, we have to go to learn decision trees in the next or second module, right? Thank you.